So today we're going to talk about a different kind of transistor, the field effect transistor. And the basic idea of a field effect transistor is that a piece of doped semiconductor will conduct if you put a voltage across it. So if you have a large chunk of N-channel or N-doped semiconductor and you put a voltage across it, a current will flow. And that's the basic idea, and the actual resistance of this chunk will depend on the doping and how long and how wide the piece of material is. So the way a field effect transistor works is that by controlling, you can control the width of this conducting channel with a voltage. So in this case, here's the same N channel we had before, but if we add p-doped parts on either side, we can, by applying voltage, make this region narrower or wider. This works because so between the P and the N is basically a diode, but in between the two there's a depletion region where there are no free charges, so no current can flow there, and so the current flowing from the top to the bottom can only flow through this region. And if we make the channel more reverse biased, make the PN junction more reverse biased, we can narrow this region. And so this is the setup for a junction field effect transistor, or a JFET. So the terminology here, the current flows between the drain and the source in the N channel. Source of N is electrons, so the electrons are moving this way, meaning the current flows this way. The electrons come from the source and are taken out by the drain, and you control the size of the channel with the gate. So you can open and close the gate. And this is the electronic symbol for it. And notice that you do have a diode symbol here. The gate forms a diode with both the drain and the source. And if you forward bias it, a current will flow, but you don't have a JFET in that case. So for a JFET transistor, you'll always want to keep the gate reverse biased with both respect to the drain and the source. The other point to make out is that the drain and source are symmetric. It doesn't really matter which is which. So as we apply a voltage between the drain and the source to get current to flow, what you have is that the gate drain voltage will be, you'll have a larger reverse bias between these two than these two, which makes the depletion region larger near the drain than it is near the source, and so you have this narrowing channel as you go up through the picture, and that eventually there comes a voltage between the gate and the drain where the channel pinches off. Now it doesn't actually go away, but it will become very, very narrow, and so this defines a voltage where this happens, which is called the pinch voltage. You raise the voltage above the pinch voltage, the channel never completely disappears, but the linear part of it becomes longer and longer, and so you have a larger voltage pushing current through this, and the resistance and the voltage go up together, so you have a constant current. In other words, once you get above the pinch voltage, you have essentially a current source, which is what we often have with transistors. So now let's consider the characteristics of the JFET in circuits. So I've labeled the transistor here with 2 voltage sources, actually 3, and note that the source is connected to ground, so VSS, as we would call that voltage source, is 0. Notice VGG will have a positive number, but because it's a negative value, this makes it reverse biased compared to ground, and VDD. All the currents are defined going in, so their sum should be equal to 0, and the differences between the terminals are labeled in the normal way. So first we consider the case where VGG equals 0, so the source and the gate are at the same voltage. That's fine. That's not no current will flow, but we don't want to make VGG any more than that. And so as we increase VDD, we will pinch off the channel, but more and more current will flow. So as we increase VDD, we'll get a rising current, and then we'll start to pinch off when VDD becomes minus the pinch voltage. In other words, we've reverse biased to the point of the pinch voltage, and from that point on, we get a constant current until we break down the diode and current starts to flow again. Normally we want to stick in this range or in this range and not have it break down. Now, so that was this case where VGG is 0. Now let's try increasing VGG, making the gate voltage more negative. As we do that, the difference between the drain and the gate is larger, and we pinch off earlier, and so we rise and we pinch off earlier, giving us a lower current when we become constant. Now, when the difference between the drain and the source is small, what we have is a voltage-controlled resistor here. And so, because we're on this linear part of the rise, and so basically by changing the gate voltage, we can change the size of that resistance in this small region. That resistance is basically given by the pinch voltage divided by 2 times the current, the plateaued current when you have 0 gate voltage, minus times VGS, this difference, minus the pinch voltage. I should note that when you have 0 gate voltage, the maximum current that you can get is called IDSS. That's this IDSS. That's the current between the drain and the source at saturation. So anyway, so this is called the ohmic region of operation because you're basically operating it like a resistor. When you get up into this region, you're in the active region. And in the active region, you have a constant current independent of the drain source voltage. So this is the drain source voltage, and the current is independent, but depends quadratically on the gate source voltage. So we always write that in terms of the current when the gate source voltage is 0, that's IDSS, and then it decreases quadratically as you make the gate more negative until you pinch it off when. So if VGS is at the pinch voltage itself so if VGG is at the pinch voltage, then you're pinched off at the beginning just with the ground source, and so you can't get any current at all then. But as you raise this towards 0, you get more and more current. So basically, and then you get desaturated when VGG is 0, and that's IDSS there. So IDSS goes down quadratically with VGS in this form. So we start with 1 when VGS is 0, and we go to 0 when VGS is VP. VP is the pinch voltage is a negative value, and so they're both negative, and we're subtracting off that as we go down. Okay, so summarizing JFET operation, there are 2 regions, the ohmic region and the active region. we sometimes call this the saturation region. That's confusing because in BJTs, active and saturated mean different things. Here they mean the same thing, which is what we normally mean by active in the BJT case. The separation between the regions is given by this line, which is given by VDS, the difference between here and here, that equals VGS, whatever this difference is, minus the pinch voltage. And so that draws this line on this plot where you have the current versus VDS. And you can get that line just by matching this behavior to that behavior. So in the active region, let me go with that first, we have a constant current. In other words, it's constant with respect to VDS. No matter what this voltage difference is, we get a constant current. And that is given by the current when VGS equals 0, IDSS, and goes down as we make VGS more negative in this form. In the ohmic region, we have the fairly complicated formula, which we'll just memorize. It still depends on this saturation current IDSS, but it grows with VDS linearly in this fashion. So it grows with VDS with a resistance that looks like this, 2 times 1 minus VGS over VP, and divided by another minus VP. But then as we get towards the active region, we have to turn over quadratically, and so we have this quadratic term, VDS over VP squared. And you can check that when VDS equals VGS minus VP, these two forms will be the same. Now, if we're in the active part of the curve, we can forget about the VDS part because it doesn't matter. It doesn't matter what the voltage is between the drain and the source. However, the current depends on VGS in that case, so we can concentrate on that, and we call that the transfer characteristic, which looks like this. As VGS is 0, we get the full current we can get out, and as we go down in voltage, we drop down with this quadratic form like this until we get to VP, and then we're cut off. All the discussion of JFETs until now have always assumed an N-channel JFET, but we can turn everything over and make a P-channel JFET with N doped semiconductors on either side, in which case our transfer characteristic just gets flipped over like this. VP is positive, and but otherwise everything else works the same. The symbol, of course, has the diode pointing in the other direction, so you'd have an arrow coming away from the junction rather than towards it. A few more notes on JFETs to notice before we go on to MOSFET transistors. Note that the transistor is on when the gate voltage is 0, when the gate source voltage is 0, so that you can think by default it's on. And the lowest resistance that we get coming through here is also when VGS is 0, and then we get the maximum current, IDSS. So when we forward bias VGS, a current flows just like any diode, but that's not the intended operation, and that the source and drain are interchangeable. So we go through those characteristics to distinguish them from MOSFETs, which we talk about now. So there are two kinds of MOSFETs, depletion MOSFETs and enhancement MOSFETs. And first we talk about depletion MOSFETs. So here is the physical model of a depletion MOSFET. We have, again, an N-channel transistor, piece of semiconductor that we're going to flow a current through, as in the JFET case. And we're going to control the size of that region with the gate. So in that way it's just like the just like the JFET. However, the gate in this case is separated from the semiconductor forming the channel by a glass region, or so there's a layer of silicon dioxide put there, an insulator, and so there's no way current can flow from the gate to the current channel. And so this is called the depletion MOSFET because it works by reducing the size of the channel. In other words, depleting it. Here's the symbol for it. The base has its own connector, which does form a diode with the drain source channel, and the gate is separated from it by what looks like a capacitor. Now, usually the source is connected to the base to make a zero voltage difference between the two, meaning that it's slightly reverse biased, that diode, at all times. And in this case, the symbol, if that's true, we can get rid of the base, and the symbol looks like this. Note that there's a heavy black line there showing that there is an open channel there by default. So the depletion MOSFET works almost identically to the JFET. So the JFET would be restricted to this region. If we put a negative gate voltage, we narrow the size of the channel for current, reducing the amount of current that can flow, or lowering or increasing the resistance. And so in this region, it works just the same. The big difference is that because the gate is insulated from the channel, we can also enhance the region by making it larger, by putting a positive voltage on it. We can do that because of the insulator. It's not a diode anymore, it's essentially a capacitor. And so even though we have what's called the depletion MOSFET, it works in enhancement mode when we put a positive voltage on it. And so we just take this part of the JFET case and keep going up. And so in the transfer characteristic, the JFET had this, and in the depletion MOSFET case in enhancement mode, we can just keep on going up quadratically. Everything else is the same, and note that that includes the fact that the MOSFET is on if we put no gate voltage, no gate source voltage difference. The equations, most importantly, the equations are the same for what the characteristic is here, and how the current depends on the gate voltage. We still call the current at zero gate voltage the saturation current. We call that IDSS. Now, finally, the last kind of FET transistor we talk about is the enhancement MOSFET. And in this case, we get rid of the channel that we had in the depletion MOSFET. What that means that the transistor is off if we don't put a gate voltage. However, if we make the gate voltage large enough, we will push the holes in this P substrate away, and we'll get a buildup of electrons right along the edge of the glass plate, making there a conduction channel. So in other words, we can turn on this transistor if we make the gate voltage large enough. So it's off when the gate voltage is zero, but we can turn it on, which is very useful. And that turn-on voltage we call the threshold voltage V sub t, which is a positive number for this N-channel MOSFET. So again, we normally connect the substrate to the source, giving us this symbol for it. Now note that unlike the depletion mode, there's no channel here. You just get the capacitor, but no extra channel. That's how you tell the difference between the depletion and enhancement MOSFETs. When you have all four connections, then there's a gap to show that there's no channel by default there. So the enhancement MOSFET works in the same way as the depletion MOSFET or the JFET, but we replace Vp, because there's no pinch voltage, with Vt. It plays a similar role, but it's a positive number. So if we look at the ID characteristic with respect to ds, if we're below the threshold voltage, we're just down here. There's no current, doesn't depend on what VDS is. And then as we turn it on, in this case, it would turn on at 2, Vt equals 2. We start to get a voltage, and as we increase that, we go up quadratically. So that's given by this. So, just it depends quadratically how far above the threshold voltage we are. And there's some constant of proportionality, k. There's no IDSS in this case because it's not on when the gate source voltage is 0. So anyway, this current increases quadratically, and again you have to match this form, this ohmic form, with this at the end, and you get this equation, which is nearly identical to the other one, but we don't have a Vp to divide by, so we just have the same k there. Again, it grows linearly in the beginning, depending on with a resistance that depends on how far we're above the threshold, and then it turns over quadratically to match at the line here. And this line is given by when we are one threshold above. So in this case, so if VDS is VGS minus VT, then that defines this line. And the resistance in the ohmic region is given by 1 over 2k VGS minus VT. You can see that has to be there from this. And the transfer characteristic looks like before, except we've moved everything onto the positive side of this plot now.